And he's going to talk about uniqueness of ground state solutions of non-local equations in one dimension.
Okay. Well, thanks to the organizers for inviting me, giving me the opportunity to talk here. The topic, as Maria said, is about uniqueness of some nonlinear equations, the ground states of those, and all I'm going to tell you is joint work with Enno Lenzmann. By the way, can you hear me? I would prefer to speak without a microphone. Okay. So if that's fine, then we will stay like this. Okay, good. So I would like to say immediately that this is a nonlinear equation that I'm going to study. I understand that several people somehow come more from the linear background. All the basic, what will be done inside the proofs, even if the statement is nonlinear, the proofs will be linear. And it's actually quite the opposite. So we would like to understand the linear analysis a lot better in order to be able to say something in the nonlinear situation. And at the end, I think I will pose a challenge here about, a spectrum of pseudo-relativistic Schrödinger operators. If we could understand this, then this would help us a lot in the nonlinear situation. So please bear with me until you reach the linear part where I guess we all feel at home. If you have any questions, then interrupt me. This is a 45 pages paper. I tried to pick some things which are which I think important. If you want to have more details, just interrupt me, right? Okay, so let's see, let's look at this nonlinear equation here. Up there it's written, it's minus Laplacian q minus q to the alpha plus 1 equal to minus q. So that looks like a Schrödinger equation for the potential which is given in terms of the ground state. Okay, so the potential V is just minus q to the alpha. We will be always interested in positive solutions to this equation. Okay, so Q is always positive, it's like a ground state. And we will also always be interested in finite energy solutions. So we always assume that it's an H1 solution. Okay, there's a little bit of small print. This power alpha that appears in the nonlinearity is assumed to be subcritical in the Sobolev sense, meaning just that it isn't too large. Okay, and so the result, the background result is that this equation has a unique solution up to translations. Okay, unique positive solution up to translations. Okay, so this theorem really has three parts to it. The first part is, there is a solution. Okay, so, how do you prove this? Well, one way to do it is you look at some quotient here. Here it's a gradient appearing. It's the 2 norm of the function and the alpha plus 2 norm of the function. Now, Gallardo-Nirenberg tells us that this is bounded from below by a positive constant. You look at a minimizing sequence, and then in the mid-70s, it was proved that this minimizing sequence will converge. And then you look at the Euler-Lagrange equation for this quotient, and there you go, you have your solution. And also from this minimization, you know that the solution that you construct in this way is going to be a positive solution. Okay, so existence is settled. Now the next thing that you do, and that's actually quite an amazing result, is as soon as you have a positive solution, it is necessarily radially symmetric with respect to a point. Okay, so that method goes under the name moving planes method. I think it goes back to Alexandrov, then Jim Sarin worked on it, and then there's a famous paper of Gidas-Nirenberg where they really advertised and showed the whole power of this method. So that's fine. So now we have a positive radially symmetric solution, and now I guess most of you would think that now it's over because now we're somehow in the ODE business. And that's it, but that's unfortunately only there where the real hard part of this theorem comes in. So you would like to prove that if you have a positive radial solution, then there is only one. Okay? And now again, many people have worked on it. I mentioned here Kaufman, McLeod, Sarin. and then Kwong, and notice that after the name of Kwong, I didn't put any points, because Kwong really settled this question. It's a complete result. It's quite remarkable, but it's also very difficult. So he used ODE techniques, some shooting methods, to show that there is really only one. Okay? And so that, I hope, settles the background, and now we will go forward. Let me just make a little side remark, because before I said something about this Sobolev subcritical case. Well, one thing is, if the alpha is too big, if you're in the supercritical case, then you don't have any finite energy solutions. And also in the critical, you don't. But what you're rather going to look at is then the equation not with a minus q on the right-hand side. So you imagine the minus 1 being the eigenvalue. But now you're looking at a zero eigenvalue equation, somehow morally, right? And then in this case, that's quite different from the situation from the subcritical case, because this equation down there has a huge invariance group. It's conformally invariant. And this leads to the fact that you can write down all the solutions. Okay, you can solve this. So that's, in a certain sense, a lot simpler. Anyway, let's go back to our equation up here. And let's talk about uniqueness of ground states when I change the Laplacian to the S. Okay, so that connects us with this workshop. For S equal to 1/2, this models some pseudo-relativistic particles. But as we will see later, it's really important to consider this equation as depending on a parameter S, continuous parameter S. Okay, so everything's the same except for this power. The Q is still subcritical in the Sobolev sense. We're still looking at positive solutions of this equation. We're still looking at finite energy solutions, which now means that they belong to the appropriate Sobolev space. Just a reminder, this fractional Laplacian is defined in Fourier space by the multiplier xi to the 2s. And what we will see is important for this question we're considering is that this power s is always between 0 and 1. Otherwise, the question is not really well posed. Okay? And well, so we're asking the question, what can one say about these ground states? Now, remember, there were 3 parts to this theorem before. First part, existence, so that works here exactly the same way. Nothing changes. Second thing is that we had this radial symmetry result. This actually took a couple of years, but I think perhaps 3 or 5 years ago, people were able to adapt this moving plane method also to this equation. So once again, if we have a positive solution to the equation, it's automatically radially symmetric. Now, you're at the third step, right? Where before we could use the ODE methods. This doesn't work at all anymore, right? So we've got to find some other way to proving uniqueness here. And let me mention, so you have 3 parameters in the game. One is the dimension. Second is the S, the power of the Laplacian. Third is the alpha, the power of the nonlinearity. Among all these 3 parameters, there's only a single point where the answer was known so far. And that's a result of Amick and Toland, namely in dimension 1, for a quadratic nonlinearity and for the square root of the Laplacian, it turns out that the equation comes from the Benjamin-Ono equation, which is a completely integrable equation, and those are just the solitons. So in this case, you can really write it's 1 over 1 plus x squared. That's the ground state you check, and then you can also prove that those are the unique minimizers. What can we say away from these points? Well, once again, there is in the critical case, you would also remove the right-hand side, then you have the conformal invariance, you know everything. But what about this equation? I think I should motivate somehow a little bit why we're interested in this. So of course there's this connection to mathematical physics when one tries to incorporate relativistic effects. I understand that this equation, especially with s equal to 1/4 and 3/4, appears in water wave theory. where you have gravitational and capillary waves. It appears also in biology, mathematical biology, and mathematical finance. If you think about it, the point is for the usual Laplacian, the heat kernel, right? That's a Gaussian. That's very fast decaying. Now for this thing, the heat kernel has only a polynomial decay at infinity. So that appears when you want to model some rare, when you want to give more weights to some rare events. Okay, so some heavy-tailed distribution. So those are some examples where equations of this type come from. I should say that these nonlinearities, again, the alpha is, for me, it's just a parameter. Things that you find typically in water wave theory are alpha equal to 1 and 2, so quadratic and cubic nonlinearity. In mathematical physics, you often find cubic and quintic linearities, and also I think when you consider these charged Bose gases, then I think it's 14/5, I think. So anyway, this is a model for us, and of course it would be nice to treat more general nonlinearities. It will also be interesting to consider a mass, the relativistic case with mass, but let's start for simplicity with the simplest thing, where the kinetic energy is homogeneous and the nonlinearity is homogeneous. Okay, so here are three dispersive, nonlinear dispersive time-dependent equations where you see exactly these phenomena, homogeneous kinetic energy, homogeneous nonlinearities. I don't want you to read all this. You might have heard this name, Benjamin Ono, or fractional nonlinear Schrödinger equations. These equations, whatever they might be exactly, they have special kinds of solutions. Some have traveling wave solutions, right, where they're the same shape, just moves along as time goes by. And the other one, the NLS equation, has solutions which are just staying there, not moving at all except for perhaps some phase. Anyway, so let's make this ansatz, or let's put these functions into these equations, and then you see if the Q satisfies the equation that I was considering at the beginning, then these functions, which depend now both on space and time, satisfy these nonlinear equations. And now what do people who study such nonlinear dispersive equations want to do? Well, they want to study global existence on one hand, or if the equation is rougher, then there is a phenomenon called finite blowup, and then they often want to understand how this blowup appears. And both questions, both the stability for global existence and when you have the finite time blowup, somehow the understanding of the profile of the blowup, this depends on understanding these functions Q and the spectral properties of the corresponding linearization. Okay, so this is certainly one of our motivations, and this also led Koenig, Martel, and Robiano to conjecture that these ground states Q are unique. And so when they expected that for any S between 0 and 1, one should have the same result as I explained on the first, recalled on the first slide. When you look back a bit in the history, then Weinstein had made the same conjecture actually more than 20 years ago, in 1987, and in the same year, Lieb and Yao, in a closely related model, conjectured that ground states will be unique, up to translations, of course. Apart from all these applications, I think there's a fundamental mathematical issue to be understood. So let's look first at the linear case, for example. We all know that the ground state of a Schrödinger operator is unique, right? And this follows, one way to prove it is to go to the semigroup and then use some positivity improving property of the semigroup. Now it turns out that the heat kernel for minus Laplacian to the S has exactly the same positivity improving properties as the usual one. And therefore, in the linear case, we know again that the ground state is unique. Now, this is the point of the talk where the assumption comes in that S is between 0 and 1. If S goes above, then the heat kernel is no longer necessarily positive. And so now that we understand, now that we see somehow that the linear case works exactly as in the local situation for the Laplacian, it's natural to try to understand this also in this case. And I think that general question, I was talking about the heat kernel, positivity of the heat kernel zone, right? That's always related to a maximum principle. And we have maximum principles for these equations. So isn't it that this uniqueness of the ground state should be much more related to a maximum principle or something instead of this locality or these ODE techniques that Coulomb used, where you somehow know that you have this, you start and from a given initial value you can solve it. Right? So that's, I think, the fundamental issue that in this joint work we try to understand. Unfortunately, what we want to do is not the same thing as what we can do. So the result that I'm going to present to you now on the next slide is unfortunately not able to answer this last question. But along the way of what we're doing, perhaps we see some things and we learn some things, and this is not the last word. Anyway, so that's the main result. Let's read this together. The main assumption that you see here is already in the first, or the second symbol here, that's the dimension is assumed to be equal to 1. The nonlinearity parameter, the alpha, there's no restriction on that. That's exactly the subcriticality restrictions that we have from Sobolev. And then what we're doing is we're minimizing this Gallardo-Nirenberg quotient that we had on the first slide. Okay, they're just scaling dictates in what a combination you should take. Anyway, so you minimize this thing, and then the theorem is that this infimum is attained by a unique function modulo the symmetries of the equation. Okay, modulo the symmetries, well, you see obviously this thing here is translation invariant. It's of course invariant if I multiply my function by 17, and it's also invariant if I dilate everything. So in other words, there is a unique positive, even and decreasing function such that any other minimizer is of the form constant times the profile function shifted by an amount C and dilated by an amount B. Okay, that's the uniqueness statement. And now, together with this theorem is something which is called nondegeneracy in the literature. That's useful for these stability properties. So what you're doing is first you normalize your profile function such that it satisfies this equation. Okay, that's the equation from the first slide. Now you differentiate this equation with respect to Q. This gives you a linear operator, right? When you differentiate Q to the alpha plus 1, this brings down an alpha plus 1. So that's a linear Schrödinger operator now. And you can look at the kernel of this operator. Okay, now first of all, when you differentiate the equation for the Q with respect to x this time, differentiate it with respect to x, well, this commutes here. Now, once again, you differentiate here. So this brings down the alpha plus 1. There's a Q to the alpha, and then there's a Q prime, right? And nothing more interesting happens here. So in other words, what you get from this is that Q prime, the derivative, with respect to translations, right, of the minimizer Q automatically lies in the kernel of the linearization. The statement of the theorem, the second statement is that nobody else lies in this kernel. Okay? Right, this could be your, I mean, a priori, this could be degenerate. I mean, there could be multiple eigenvalues, but it isn't. And that's, as I said, that's important for different things. So even though we're presenting this as the second part of the theorem, it's actually somehow this is really the crucial point. And as I will explain to you, we're really doing this first and then deducing the uniqueness afterwards. Concerning the assumptions of this theorem, well, I already said that it's perfect with respect to alpha. It's not so perfect with respect to the dimension, but you see this. You will see on this talk has about 12 slides, something, and only on the very last slide this assumption n equal to 1 comes in. So most of the arguments, the whole strategy works in the general case, and then there's this challenge, this about linear shielding operators that I mentioned at the beginning, which somehow is related to this not so nice assumption. Okay, what I consider somehow more, well, perhaps I should also mention that there is ongoing work in this direction, also jointly with Luis Silvestre and of course Enno, and we're optimistic that we can do something for positive n. What I think is more important here for us is, you see, we prove not really uniqueness for positive solutions, but really only for these energy minimizers. We do it a little bit more general, as you will see on the next slide, but nevertheless, somehow there is no restriction needed in the local case, and so the question is it true that any positive solution is necessarily already an energy minimizer? That's true in the local case.
You know, I don't remember the name, but there was somebody, a student of Nuremberg, who proved before the result of Bonn that there was uniqueness for the energy minimizing solution, not for the positive solution.
I see, okay.
Maybe you should look at that.
Okay, thanks.
I don't remember the name, but I can
okay,
find.
Okay, thanks. Okay. Yep. Good. So, right, that's where we are. Let's move on. This is now, I'm going back to this non-degeneracy statement. I've told you that this is somehow the machinery that drives the whole proof. And let's read this again. So Q is a positive solution, and then by moving planes and so on, we know that it's necessarily even and decreasing solution of this operator. L plus, remember that was the linearization around the solution. And now, since this is a Schrödinger operator with an even potential, we know that it leaves the even subspaces and the odd subspaces invariant. So when we're talking about the kernel of this Schrödinger operator, we can look at the kernel on even functions and on odd functions. So let's talk about the odd functions first. And let's remember also that I said before that the derivative of the function belongs to the kernel. Now, moreover, the derivative, the ground state is a decreasing function, so the derivative is a strictly negative function on the half-line. So therefore, we are exactly in the situation for Perron-Frobenius. We have an operator with a sign of as an eigenfunction, so it's got to be the lowest eigenfunction, and it's got to be simple. So from this argument alone, we know that if we look at the kernel of the operator restricted to odd functions, then this is exactly the span of this function Q prime. Here we use the positivity of the heat kernel and also some monotonicity. Okay, so that's fine. What's to be done, and what's really the most difficult thing, is to look at the operator restricted to even functions. Now that's a lot more complicated, because you can just, here this is the equation, right? Dot this into this is the, let me do it like this. This is the linearization. Now let's compute the expectation of the linearization in the state Q, right? So because of the equation, this term, the 1 here and the 1 are 0. That's just the equation. But there's this leftover alpha when we differentiate it. So therefore, this expectation is equal to minus alpha times this integral. The integral is positive, so this thing is negative. So we know that this L plus operator has, from the variational principle, at least one negative eigenvalue, strictly negative eigenvalue. Okay, so now at this point, I can state for you the real non-degeneracy result that will be crucial in the following. So let's assume that we know from somewhere else that this L plus operator has exactly one negative eigenvalue. Okay, somebody gives us an upper bound. And then we can we infer that 0 is not an eigenvalue. Okay? So this tells you somehow, if you know that the second eigenvalue is non-negative, it has to be already positive. You see that this is a rather non-trivial result. There's something happening in the proof of that. And it's important when we apply this that we do not require the Q is a minimizer. It's not an energy minimizer. The only assumption is that we have this bound on this thing called Morse index. Now, let's look at the local minimizer. Well, then so J is this Gallardo-Nirenberg quotient, all right? We differentiate twice with respect to a perturbation, and then we write this out, and this condition says exactly that the operator is non-negative on a subspace of codimension 1. So this, for local minimizers, we get this assumption. Okay, so in particular, taking this little computation here together with this statement, we get the non-degeneracy theorem as stated in the statement as stated in the previous theorem. Okay, so this is what we really want to prove. Strictly non-negative positive, non-negative second eigenvalue implies strictly positive second eigenvalue for the linearization under the yeah. Okay. So let's take this theorem for granted for the moment. I told you that this is really something to be understood. Let's see, once we have established this non-degeneracy, how we can argue to get the uniqueness. So the argument is, I think, not new at all. It's somehow you make a deformation. And the deformation parameter that you have is this parameter S, the power of the Laplacian. Okay? So we think we start at a certain number S naught, and alpha. Alpha is fixed throughout the moment. The S naught is fixed, and we think we have a certain function Q, which is a solution to this equation, which has not a zero eigenvalue when restricted to even functions. Okay, now what we can do is we can apply, that exactly guarantees us that we can apply the implicit function theorem, and then we can start solving the equation where S is the parameter. And so we get a branch of functions Qs, at least in some neighborhood of where we started, well, which connects our or starts at our initial Q, and well, which is just a family of solutions. Now this branch has a lot of nice properties. When you start with an even function, then all the functions along your branch stay even. Also, when the functions are even and sorry about that. They are even by construction. Now the point is, when they are positive at the beginning, they stay positive. When they're decreasing, they stay decreasing. Okay. Now here comes the key fact. Namely, if at the beginning you only have one negative eigenvalue, one strictly negative eigenvalue, then you always have one negative eigenvalue along the branch. That follows from this non-degeneracy, right? Watch the lowest eigenvalue and the second eigenvalue. Watch them move. Somehow, the lowest is down here. The second one is at the beginning positive, but somehow when it's non-negative, it's strictly positive. So this second never can go down to zero. And since we already know that there's always one negative, the lowest can't go up either, right? So the second always stays above, the lowest stays always below zero. So we are always in this situation where we can apply the implicit function theorem and where we can continue the branch. All right? Now something might happen because, you know, these things could just make funny things. The things could either spike up or just disappear. They could do something. So I'll talk about that later. But for the moment, believe me that we are able to continue with respect to this S all the way up to 1. So then, the function that we get at the end, that's a function Q1, which satisfies the equation from the first slide. Right? It's just a Laplacian. Now here, we know, actually in one dimension you don't need Kwong. In higher dimensions you would need Kwong. In one dimension you just sit down and solve the equation. You know that this equation has exactly one positive solution. So wherever we started from, we could find a branch which connects it all the way to one fixed function. Now once you have this statement, the uniqueness is obvious, right? Because if you start with two functions there, you connect both functions to this given function, But here at this point, well, it's first of all, it's the same, but also it's not only unique at s equal to 1, but it's also non-degenerate. So you could solve backward with the implicit function theorem. So they have to be already the same before that, and then just by this non-degeneracy again, they have to be the same always. Okay? So that's the idea. We go back to the one case that you understand, namely s equal to 1. So what I have to explain to you is that somehow that you can extend this branch all the way up to s equal to 1. So well, what you do, you define just a number s star, which is the maximal s up to which you can extend it. And then what you try to do is you want to argue by compactness, right? So you have, remember in this equation, this comes naturally with 3 norms. One is a kind of kinetic energy, which is this Laplacian to the s over 2qs, the 2 norm, then the 2 norm of the function, and this nonlinear alpha plus 2 norm. Now, from the equation, you have one identity between these 3 quantities, right? Just multiply the equation by q and integrate by parts. That gives you one identity. The other one is a thing which is called Poroshaev identity, or I don't know, Virial theorem. So what you really do is you multiply the equation by r q with respect to r. This gives you yet another identity. So you have 3 quantities, you have 2 identities. So it shouldn't be too complicated to control those. And moreover, because of Sobolev inequalities, you can easily get upper bounds. So at the end of the day, the only thing that you have to do is you have to find an upper bound on one of those, say on the 2 norm of QS. So that if you think about it, so you have a lower bound on the alpha plus 2 norm, and on the 2 norm, you want to get an upper bound on the 2 norm. This means you have to rule out that these things just vanish. It goes down. And this is really the point where you have to sit down, and the way we're doing it is using Grunwald's identity. So you somehow differentiate this norm, and you control its change in terms of what it is. I should say that this is really the moment in the proof where we do not use energy methods, where we really work with the equation, where we have to get more regularity than only the energy.
Excuse me, what are Pohozaev identities?
It's a Virial theorem. It's, I mean, several people in several communities have discovered it several times. And, okay. So, anyway, this is the point where you have to sit down and where you have to prove something, but that's it. Once you have these uniform bounds from above and from below, you can pass to a limit, and then the limit exists, satisfies the equation, and now you can argue what happens with the second eigenvalue of this limit, and now you know, well, along the limit, you still have one negative one. If it would have, it was all the time, it was bigger than 0, so it could have been 0, but that's excluded by the non-degeneracy. Same argument as before, right? It can't. The important thing is that we really have this theorem that says that no crossing can occur. All right. So now so far for the linear part. Now let me come back to this linear analysis where we have to understand fractional Schrödinger operators. Now this is the point where the dimension equal to 1 assumption will come in. I want to prove the non-degeneracy. So what I want to look at is a fractional Schrödinger operator minus Laplacian to the s plus v. And the v is small at infinity. I have a couple of eigenvalues below the bottom of the essential spectrum. And now I look at eigenfunctions, and I know that the first eigenfunction is strictly positive. Now the question I'm asking is, how many nodal domains does the kth eigenfunction have? Looks like a very classical question, right? In the Laplacian case, in dimension 1, Sturm tells us exactly the number of nodal domains. In higher dimension, Courant gives us at least an upper bound. Now, as far as I know, this question has not been studied for this relativistic operator, and that's a challenge. If we could prove here something, actually, what I would like to prove is that the second eigenfunction of a fractional Schrödinger operator has exactly two nodal domains. Or say, I would be happy if this could be proved for radially symmetric and symmetric increasing potential. That's the question. And all I'm going to tell you here is somehow our hard-working attempts to get close to this statement. Unfortunately, we are rather far from it. What we do is, however, enough in one dimension. So let's go through that. Dimension is 1. That's this assumption. We have the power s between 0 and 1 arbitrary. We have the kth eigenvalue being an eigenvalue below the essential spectrum, a corresponding eigenfunction psi k, and then the statement is that this has at most 2 times k minus 1 sign changes. That's for k equal to 1, while it says the ground state doesn't change sign. For the first excited states, already it says they could have 2 sign changes, which is bad, right? Which is not the thing that you would expect from the local case. Now, and well, I guess, I mean, the hope is, of course, to prove something for general k, and that it should again be linear in k with the coefficient 1. People, I said before, have not studied this question before. That's not completely right. What people have looked at is the special case of the fractional Laplacian on an interval. And I should tell you what that is. That means you look at functions which are 0 outside the interval, then you extend them by 0 to the whole space, you Fourier transform, you multiply by psi to the 2s, and that's the operator, okay? So it's an infinite potential. Now in this special case, people were able to show that the second eigenfunction has exactly 1 nodal domain, and the third eigenfunction, has 2 nodal domains, and the third eigenfunction has exactly 3 nodal domains. That's what is known. That was a result by Banuelos and Krusnitsky, and I'm mentioning here Kwasnitzky because what Kwasnitzky can prove, which is somehow close, again, only in this interval case, right? Only in the interval case. Kwasnitzky can prove that they're alternatingly even odd. Also, this statement is not known in this for the general Schrödinger operators. All right, now how do Enno and I do this? We somehow resort back to the local, to what we know about local equations. Now, here's a variational characterization of the kth eigenvalue in terms of a local Dirichlet form. So what we do here is we add an additional variable y, and we're looking at the Dirichlet integral, perhaps with some weight, in the upper half space. And we have the potential sitting only on the boundary of the half space. All right? And well, so you minimize this under the normalization on the boundary and under the condition that u restricted to the boundary is orthogonal to the space of these functions. Now that's not hard to come up with, right? You just minimize, before you minimize with respect to u, you minimize for a given boundary trace, you minimize with respect to how the function should look like in the upper space. And then you know that this extension is gives you exactly the fractional Laplacian. I think ideas like this have been around in the Russian literature since the 50s. There were some remarkable results of Swarsky and Graham, where they used something like this for the ground state, and then Caffarelli and Silvestri also discovered it in yet another context about free boundary value problems. So what we did is somehow we generalized their results to higher, not only to the ground state, but that it's just a simple observation that it immediately works also for excited states. Now, why is this good? Good thing is that here you have a local kinetic energy. So now what you can do, assume that you're, right, so you look now, you have the trace given, and you look at extensions, all possible extensions of this function. What you really do is you prove that this extension of the function has at most k nodal domains. Now there, the old Courant proof works, right? Because assume that you have too many nodal domains up there, you just remove one, you cook up a trial state with those, you see that you get exactly the same energy, and therefore by unique continuation, it's a contradiction that you've taken out something and that it's 0 there. Okay, so therefore, the point where you are now is you have a function down there. You have an extension, and you know, say for the second eigenvalue, that the extension, that's our original x variable, that's the extended y variable, that it has 2 nodal domains up there. Now, what could happen, what you would like to happen is something like this, for example. Then it has 1 plus here minus there, for example, 2 nodal domains up there. The bad thing, what might happen as well, is it could be plus here and minus there. 2 nodal domains in the upper half plane, but 1, 2, 3 nodal domains down there for the trace. Exactly this thing is where this factor 2 comes from here. And this, if you think a little bit about this, now all I'm said up to now in this talk is valid for a general dimension. The only thing, you sit down and you wonder, what does it mean if you are now in the half space? What does it mean having 2 nodal domains in the half space? What does it mean for the boundary trace? And that's where we need this assumption. Anyway, let me continue here. Using this fact here, if we know that v is an even function, and we assume that the second eigenvalue has an even eigenfunction, okay? So this does not happen for the Schrödinger operator, for the local Schrödinger operator. We can't rule it out here. Well, then we know that the psi2, the worst thing that can happen is this picture, then changes sign exactly once on the half line. All right? And now, having this information, let me tie the things together. Let me show how this result about linear Schrödinger operators implies this non-degeneracy statement that we had before. As before, Q is a positive solution of the equation. L plus is the linearization. We assume that that the second eigenvalue is non-negative, and then we want to prove that it's strictly positive. Now the proof here, we learned it from a paper of Chang, Gustafsson, and another authors, but I think it's a rather standard argument in the ODE literature, or of this arguments of this type. So assume it's wrong. Assume you have a 0 eigenvalue. Now, the good thing is you get 2 orthogonality conditions for free. All right. So the first orthogonality condition here, that just comes from integrating this equation against psi. Okay. And then you see it's again because you have this leftover alpha term. That gives you that the integral of psi against q is to be 0. Now the other thing, and that's where this homogeneity of the kinetic energy of the nonlinearity comes in. You also know that psi is orthogonal to q to some power. Good. So what you can do is, you can take linear combinations of these 2 things. So here I took q to the alpha plus 1, right here, these together. And then this is just a constant times this function q. And now, well, since whatever r I take, I just take the constant of the form that it's the function q at r to some power. But whatever it is, it's always 0. But let me now choose this value r a little bit carefully. I'm going to choose the r exactly at this point where this eigenfunction, the second eigenfunction, changes sign. Why am I going to do this? Well, because I know that before the q is a symmetric decreasing function. So if I'm before this value of r, the q minus its value at r is positive, after it it's negative. So in other words, the q to the alpha minus q of r to the alpha changes sign exactly at the same place where psi changes sign. So this product is positive. Remember, q is also positive. So here you're integrating something which is strictly positive all the time, and then you have a contradiction. Okay? So this proves the non-degeneracy. I hope I've told you how this 0 comes in. You see, I guess, that everything works in higher dimensions if you have this other thing before. And if you have any ideas, then please let me know. Thanks.
Questions? I have a question actually. To construct a branch, you could use topological degree
No, we just, well, perhaps one could do, but we do it really by hands, just implicit function theory.
Other questions?
Hmm?
Well, if not, thank you very
Okay.
much.